All right, second to last problem, 2019 Physics C. I wanted to do the most recent. That actually kind of means, folks, that they're probably not going to be dealing with the same sort of concepts. But I wanted to provide you with the most recent ones because I just want you to show you how annoying they are and how they just go on and on and on. They have become terrible writers of questions as they just get more convoluted and more text that doesn't help anything. So have fun. Okay, so I've got a platform, rotational inertia IP, rotates freely without friction. I'm just going to circle that because that's important. Small motor-driven wheel. Right, they're going to ask us about error. There's our error. Rotate the platform. The wheel has radius r. Touches. Okay, so that's providing a torque. D. The platform starts at rest. The wheel exerts a constant horizontal force magnitude F tangent to the wheel. Time t. The wheel stays in contact with the platform without slipping. So derive an expression for the angular speed. Okay, so in other words, I need to do sum of torque, so I know what the torque on this is. So sum of torque is equal to I alpha, so we get an expression for alpha. So it's that constant force, it's the torque due to that force. The torque just due to that force is equal to I alpha. That's all I have. So it's the force times d, because that's the lever arm distance, is equal to IP. I believe that's what it's called, alpha. Alpha is equal to FD over IP. And I want omega, so look, F, D, those are all the things I'm allowed to use. Now I'm just going to use, it's a constant force, so I can use kinematics, and therefore I can say omega final is equal to omega initial plus alpha t. I'm allowed to use t. Yep, great. So I know that that's starting at rest. So omega final, or omega p is what they're using, is equal to FD over IP, and then over that time period, delta t, and that's A. Okay. B, determine expression for the kinetic energy of the platform the moment it reaches that. All right. So KER equals 1/2 I omega squared. This is really not, this is, okay, 1/2 IP, and then FD over IP delta t quantity squared, and so that's going to be 1/2 IP F squared D squared over IP squared delta t squared. One of the IPs goes away, and so I have F squared D squared over 2 IP delta t squared. Alrighty. Okay, here are done. Derive an expression for the angular speed of W omega W when it's reached angular, what? When is W? Derive an expression for the angular speed of the motor-driven wheel. Oh, okay. Oh, okay. So here's the thing. This has a larger radius than that does, but they're in contact, so there's no slipping there, right? So the velocities of those 2 points have to be identical. So, the velocity of the big wheel has to equal tangentially, has to equal the velocity of the small wheel tangentially, and we know that this is omega p and then times the radius d, and this is omega little wheel times its radius little r. Oh, that's almost clever. So omega r, or w then, is omega p, which we have as fd over ip delta t times d, right, divided by little r. And just to neaten that up, fd squared delta t over ip little r. Boom. Okay. All right. When the platform is spinning at omega p, the motor wheel is removed. Okay. The student holds a disc directly above, concentric, it is, okay. Rotational inertia p, the student drops the disc. Oh, okay. So in other words, they're going to skid a bit and eventually they'll come into equilibrium. So here, the shape of the thing has changed. We should be thinking angular momentum. Li is equal to Lf because the net external torque is equal to 0. So why is that? Not that there's no torque. There's actually torque due to the kinetic friction between these two over the time that they're coming together. So they slip for a bit, and then when eventually this thing slows down and that speeds up, eventually they'll snap together at some omega, and that is omega f, right? So here's what it is. It's IP omega f, that's the term for this, plus IP, that's the term for the top one, but its initial omega, actually this is omega p, is 0, right? Because it's just dropped. And then finally, we know that this is just going to have an I of 2IP, and then omega f. So very simply, omega f is half omega p. And I can leave it in terms of omega p. Great, done. All right. Whew. Oh my God, kidding me. So, student now uses a rotating platform. Okay, so we have a value, determine IU, an unknown object about the vertical, it passes through the, platform's rotating initial I, then dropped the center. Okay, so it's doing it with just different things. Trials are repeated for different values. Okay, so in other words, going back to what we said before, it's IP omega p plus nothing, because it's just dropped, is equal to IP plus this new I, whatever that is, IU, omega final, right? So omega final, omega initial. Okay, great. So if we look at this, we can see that omega final divided by omega initial, or so this is initial and this is final, right? That slope has got to be equal to, if we solve this for that, it's IP over IP plus IU, right? Which is a constant as long as the object has a constant I. Okay, great. So that's what's going on there. So that makes sense why that's linear then. Yes? Yeah. Okay, cool. What did they want us to do? On the graph, draw a straight line. Jesus Christ. Now I understand why my students last year told me like literally no one finished this, because the other questions in 2019 were all so long, and then you get to this nonsense after, using straight line, calculate, okay, so in other words, you gotta find the slope. This is all very time intensive, right? So slope equals, that's a good point. By the way, since you're using points, you should definitely cheat a little bit and like see if it's reasonable to get it through 0, 0, because that just makes calculating slopes so much easier. So I'll use those 2 points there. So it looks like I have 3.4 radians per second. Oh yeah, all the units are going to cancel out. Over, that's about midway, 2.5 radians per second divided by 8 radians per second minus 6 radians per second. So that is 0.9 divided by 2, or 0.45, right? So that means IP divided by IP plus IU is 0.45. So let's fill in what we know. That means 3.1 kilogram meter squared, 3.1 kilogram meter squared plus IU. Okay, multiply things across. Okay, 3.1 times 0.45, so 1.39. So this is the work for, what is this? CI and II, right? Yeah, okay. So 3.1 is equal to 3.5 plus 0.45 IU. So apparently IU is 3.79 kilogram meters squared. Done. Okay. Now, there's more. My God. The kinetic energy of the spinning platform before it drops is this. The total kinetic energy, what is that? Which of the following is true? Oh, so the final kinetic energy is less than the initial kinetic energy. Work non-conserved is not equal to 0. Friction does work. Okay, does, let's be negative work. One of the students observed the center of mass is not actually aligned. Is the experimental value of IU greater than less than O? Okay, so if it's not aligned, So that means that really that IU term would have been what the actual ICOM is plus an MD squared, right? Because it would be shifted or larger. So what do we want to know? Is the experimental value of IU greater than, less than, or equal to the actual value? Okay. Oh, it would be greater than because it is the actual IU plus an MD squared shift term because parallel axis. Oh, that question was a bear. It just went on and on.